Today's lecture is a continuation of chapter 2, shallow foundations. In the previous lecture, we were discussing an introduction for all types of shallow foundations. We are not speaking about a specific type of shallow foundations, any type of shallow foundations. Why I'm saying this? Because we will have a special lecture for a special type of shallow foundations, which is the isolated footings, as an example for shallow foundations. However, in this lecture, we are just describing what we should, the idea of shallow foundations, what we should do to design any type of shallow foundation, just a general rule. We discussed how the load is transferred from the reinforced concrete base to the plain concrete base below it, whether it is included in my design or I'm just putting it as something like a barrier between the ground and the foundation, the reinforced concrete foundation or not. Anyway, it was just introduction, just discussion. We reached till slide number 11. This is slide number 11. Today we are going to continue the rest of the design. I think this is slide 11. Yes, this is slide 11. We said that to design, I'll just say very quickly, to design a foundation based on our Egyptian code, we have to know that we are going to use two codes. We are going to use the code for shallow foundation, for soil mechanics, and the code for reinforced concrete. To use the code, because foundation is actually the interface between the soil and the structure. So the interface between the soil and structure needs the code for the soil and the code for the structure. In our case, we are going to use the code for soil to design the area of my foundation. What is the dimensions of the foundation in terms of area, length and breadth? Because this is the part that is in contact with the soil. So in my geotechnical code, we use allowable loads, not ultimate loads. So I take the allowable load, divide it by the bearing capacity of the soil, how much the soil can take, I will get an area. This area will be the area of the foundation. Now I stop using the geotechnical code and go to the reinforced concrete code. I know the dimensions, I know the area. Once I know the area, then I can design the rest of the footing, which is the depth of the footing and the amount of reinforcement. This is completely a reinforced concrete part. So I go to the code for the reinforced concrete. They use the ultimate load. So I take my previous allowable load, multiply it by 1.5 to get the ultimate load. Then continue the design. I use this load instead of the other and continue. In future, when we use ultimate load in our geotechnical code, then we are going to use one load from the beginning to the end. So this is a temporary case that we are facing, that we have to live with it till both codes use the same load. Once here we just calculated the moment on the footing. Once I calculate the moment on the footing, then I can use this moment to design the depth of the footing and the amount of reinforcement I need. So I assume I have a section here, calculate the moment, the actual moment acting on my footing. I take this moment, I use it in my design. But before we go into design, as a concrete section, there are some checks that we should do. It's not just depth and area of steel. There are some other checks. What are these checks? There is a check for something called shear and check for punching. This you might have taken in structure, in reinforced concrete section designs. So I need to check here for calculating the bending moment, and we said that we are not going to calculate the bending moment till the center line of the column. Why? Just to make some reduction in the cost, because I can calculate the moment just on the edge of the column, because actually this is the critical section. Once I go inside the column, it's another section. The section is not just a rectangular section, it's a T section with a big column, so it's another thing. So I can use this reduced moment in my design. If you use the one inside, it's correct, but you are paying for nothing, so it's better to use this one. So now this is the moment, and I need now to calculate the depth. Once I got the moment, then I need to calculate the depth. There is an equation. It is given here. You can use your equation if you, in reinforced concrete design you have another equation, use it. This is the one I am presenting, but if you in design of reinforced concrete sections you have another equation for the design for getting the depth of the section, it's okay. This equations uses the M, the ultimate moment, of course, not the working, and uses FCU of concrete, B, the breadth of the footing, to calculate the D. D is the depth of steel in the section, not the total depth of the section. So if I have D, if I calculate D, then I can add to it the cover below the reinforcement, and I get the full depth or the T of the section. So this is how we calculate the third dimension of the footing, which is the depth or the T. Now, if I go to calculate the amount of steel, then I will be wasting my time, because maybe it is not, this depth is unsafe in shear or punching. So I have to check first shear and check punching. If they are both okay, then I can go and calculate steel. So just postpone the calculation for a while till you make these two checks. To know what is the difference between shear and punching, we have to understand what is the difference between shear and punching. I think we said it in last lecture, but I'm going to say it again. If I have a bar of chocolate and I tell you, give me a piece, or I want to give you a piece, if I go to the edge or the corner and I use my two hands and break a piece of the bar of chocolate and give it to you, then I'm shearing the bar of chocolate. But if I put the bar of chocolate on sand and I put my finger on top of it and I in the middle and I push, then my finger will penetrate the bar of chocolate. So this is punching. They are both type of shear, but the shape of the shear is different. One, you are shearing part of the section away from the other section, so that the bar of chocolate or the foundation have the right to choose the critical section, because it will be broken trying to find the critical section, the weakest section. So this is in case of shear. But in case of punching, I am forcing the bar I want to penetrate it in a special location. So I have to penetrate this location. It's not the choice of the foundation or the choice of the bar of chocolate. No, I am fixing the location. I am pushing here and I want to shear it at this location. So it is the same idea, but a different way of doing it. So usually I check the shear capacity of the section and compare it to a value. So I have here, in this case, I'm checking shear. Shear, it means that I am trying to separate part of the foundation from the whole foundation. Which part of the foundation that I can separate? Is it this one at the early start of the footing, or if I go inside, it will be easier, because the deeper I go inside the foundation, or if I go inside, it means that I'm adding more load. So if I tell you, try to break the bar of chocolate at the early edge, you will find it very difficult. But if I tell you, just go inside a little bit and break it, it will be very easy for you. So this is the same idea. But here, take into consideration, you have a limit to go inside. You can go inside till a certain place. Beyond it, you will be affected by the effect of the column, because the column has some load, and this load is pushing the foundation down. It starts from this point and go down like this with an angle. So it is preventing you from shearing anything below it. If I have something and I am pushing on top of it, you cannot shear it. You can shear it only if you are pushing away and there is a cantilever part. But below what you are pushing, you cannot shear. So this is the same idea. So this column prevents you from shearing below it till a certain distance. Take it d by 2. D is the depth of the footing. So I go all around the column with the distance of d divided by 2, and I say that this area is guarded by the column. The column will prevent any shear in this area. So the first section that can be sheared, the critical section, will be just on the at a distance of d by 2 from the column. So I check from both sides of the foundation, from this direction and from the other direction. You remember that we said that it is better when we are choosing the dimensions of the footing that the difference between the length and breadth of the footing to be the same like the difference between the length and breadth of the column. If you remember, or maybe I said it or I did not say it, but anyway, I'm saying it again. When you are choosing the dimension, you remember when we were designing the area of the footing, we only get an area. Divide the working load by the allowable stress of the soil to get an area. I have the choice to choose any dimensions. I have area, that's all. If I have, say, 8 meters square, 8 meters square, maybe 8 by 1, 4 by 2, any 2 dimensions will work. But what is the difference? The difference will be in the cantilever from both sides. But if I take the difference between the length and breadth of the footing to be the same difference between the length and breadth of the column, then in this case, the cantilever from both sides will be the same. This is more economic. If you have a footing and you have the cantilever from all around with an equal distance, this is the optimum design for this case. So, and also it saves your time in design, because you don't have to design two directions, just one direction. The other is typical. So in this case, if you have the cantilever length the same, then the shear, you just check shear one time at the area that has the length of the column. I will show you. I don't think there is a plan here, but suppose we are going to use this plan now. If I have, this is the long direction and this is the short direction. The cantilever here is the same as the cantilever here. Which one to check for shear? For this short distance or for this long distance? For the long distance. So I know which one to use. I know that I will use this because at this area I have bigger value of load. The cantilever is the same from here and here, the same. I don't have the only comparison. Use the longer dimension. That's all. So I take the longer the dimension, and so this will be the shorter dimension. The longer dimension is in the perpendicular view. So now I calculate the amount of load that wants to shear the section. The amount of load is the actual stress here multiplied by this area. So I get the load. I take this load divided which area try to prevent you from shearing it. Yes, below the column you cannot shear, but starting from the area where you can shear, what resists the shear? This area resists the shear. Which area you are going to shear? I'm going to put a load on which area? Which area is resisting my force for shearing? It's this thickness by the perpendicular dimension. So I take the load, divide it by this area, I get the shear strength, shear stress on the foundation. I calculate, I compare this shear stress with the allowable stress of the concrete. If it is below the allowable, then I'm safe. If it is higher, then it is unsafe. What should I do? The load is the same, but I need to increase the area that resists the shear. What can I do? I just increase the depth. That's why we said, don't calculate the steel now. Wait till we check the shear, because we may increase the depth of the section. So now I have to check this. I calculate this, which is the actual shearing stress on the section, and I calculated, compare it to the allowable given by the code. I compare both. If it is less, then I am okay, and I proceed to the other side, to the other check. If not, then I have to increase the depth again and calculate it again. So this is I think this is the equation for the allowable, and I compare both together. If I am below, then I am okay. Now I go to check punching. We said punching that we are going to push on the foundation to break it from inside, to shear it from inside. So this is the column that is pushing inside. What will be the critical section? The critical section also will be at the edge of the column, but it is not really at the edge of the column because the column is pushing a load and this load is dispersed below the column. As we said that from this area, the load go and is dispersed with an angle, say 45 degrees, and all of this area is affected by the load of the column. We said that, assume that the critical section will be at a distance of d by 2. But in this case, it's not shear, it is punching, so it will be d by 2 all around the column. In the other case, if you remember here, we moved d by 2 in one direction because we are shearing just a portion. But in punching, we are punching the whole area. So I just go from this column, this is A and B, the dimensions of the column. I go all around it with this dotted line, which is at a distance of d by 2, d over 2, from the edge of the column. In this case, this represents the area that can be sheared. You follow me? What is the area? This is the length of the area. The thickness of the area is what? Again. So now we go d by 2 all around the column, and this is the area that will be resisting my punching. And as we said, where is the area? It is this line, this broken line that is rectangle, multiplied by the depth of the footing. This is the area that is resisting my shear. The same, I will calculate the load that is causing the shear. In this case, it's the load of the column because it's the whole load of the column. It wants to shear the whole foundation. And I check and I calculate this area, divide the load by the area, I get the punching stress, the actual punching stress, compare the actual punching stress with the allowable stress given by the code. If I am below this value, then I am safe and I can proceed to the next one. If not, then I have to increase the depth again. Once I have calculated, of course, these are I'm just giving you the formulas just to know it. You are not going to be asked to calculate steel because we are geotechnical. We are not going to calculate the steel. We are just we'll so we will just calculate the punching stress, compare it to the allowable. If it is safe, then we can proceed with the to go to the next step. Of course, these are all the equations for the punching. What is the allowable? What is the shear? The actual, and we compare both. These are all for the punching shear. Now, if I reach this location or this position with safe, I calculated the depth of the section based on the moment, and then I checked shear and it is okay, checked punching and it is okay, then I can calculate now the steel. I can calculate now the area of steel. So I use the area, the equation that gives you the area of steel. If you use a different equation in your structural reinforced concrete course, use it in this design. I just any equation used for calculating the steel, the required steel in a concrete section. So I'm proposing this equation to get the steel. Of course, when you calculate the steel, you have to take in your mind that there is something called minimum area of steel. You can calculate the steel, but sometimes when you calculate the steel, you get a very small amount. This very small amount is not adequate for any section. For this section, it needs a minimum amount of steel. This is another thing from your concrete design of sections. You know that there is something called minimum steel. Any concrete section, if I put steel and I want this steel to be working, it has to be a percentage of the area of the section. There is a minimum value for the steel. So this is the equation for the minimum steel. The minimum steel, according to the code, it is 1.5 multiplied by D, or 5 phi 12 per meter. Anyway, this is we'll discuss this when we come to detailing. But what you have to know now, that there is a minimum value of steel. If I calculate the required amount of steel and I get a value less than the minimum, then I will have to use the minimum, because even if the moment is zero or a very small moment, there is something that should be used in this section to avoid other things like cracking, and it's something related to design of reinforced concrete sections, not related to our design. This is an example for a chart that gives you the area of steel directly. You just there are here parameters. This is J and the D and everything. You put it in this chart and get the area, or you use the equations. Okay, these are the equations for the allowable stresses in case of shear and in case of punching. What I should be given to design any load, to design any foundation, I should be given the foundation load. I should be given the allowable bearing capacity of soil. I should be given the column dimensions. I cannot proceed with the design of the foundations. I don't have, it's not enough that you have the column load. You have the column load and you have already designed the column, because we have just said that it is better for the foundation that the same cantilever we have from both sides. So how can I adjust the cantilever if I don't have a design for the column? So the column should be designed. Then I assume things. I assume the thickness of the plain concrete. I'm going to use plain concrete in my structural design or no? Will I use just 10 centimeters, 15 centimeters as something, in Arabic we say فرشة نظافة. It's just a barrier between the contamination of the ground and the steel and the concrete that I don't want them to be contaminated with soil. So, or I'm going to use a big PC to reduce the reinforced concrete pad. So this I assume I can this is not imposed, this is can be assumed. It can be assumed, and FCU and F yield, they should be assumed. You assume what type of concrete and what type of steel. This is a table for the comparison between in case I use, according to the Egyptian code, 20 centimeter is the minimum thickness of plain concrete in case you wanted to be included in your design. So less than 20 centimeter, then it is just for فرشة نظافة. More than 20 centimeter, then you can use it in your design. So these are the differences, what you are going to do. The main difference is that when you have the column load and you divide it by the allowable bearing capacity of soil, you get an area. This area, in case you have plain concrete that is working with you, the thick plain concrete, then the calculated area will be the area of the thick plain concrete. But if you have plain concrete that is very thin, then in this case, the area that you have just calculated will be the area of the reinforced concrete. Is this understood, or I should repeat it again? Because if it is not working, then you ignore it, you don't see it. You just add it in the drawing, that's all. But you do not see it at all. So this is the main difference between them. One is working and the other is not working. This summarizes all the minimum values given in the code. What is the minimum dimension of a footing? Can I take a footing that has a dimension that is less than 80 centimeter? No, the code say no. The minimum dimension of a footing is 80 centimeter. Can I have a thickness of a plain of a reinforced concrete that is less than 40? No, and so on. These are the minimum cover for below the steel is 7 centimeters. The minimum steel for any section, we just said this, is 5 phi 12 or 1.5 d of the section, and so on. These are all how many bar of steel I can use in 1 meter. The minimum is 5 because I don't want the distance between the bars of steel to be more than 20 centimeters. This ends up our lecture of today. Our next lecture will be the bearing capacity, and we will continue it later. Thank you.